And I want to thank Jeff and the McClung Museum generally, the staff, for inviting me down here and being such wonderful hosts for the couple days I've been here. How many of you have actually seen the map exhibit? Can you raise your hands? Fair number. Okay. Well, I urge those of you who haven't seen it yet to go and see it. It's a really fine collection of very important maps to be assembled in this spot, along some great maps of North America and the world, and some very interesting maps of Tennessee and your area. So by all means, go and see it, and hopefully a few of the things that I'll talk about today will help you to appreciate it more. My topic today, how did they do that, comes from what I think is a very basic question that people ask when they look at maps. We've all had the experience of standing in a field or on a seashore and looking out and thinking, now how would you go about mapping where I'm standing? How could that happen? And the fact of the matter is, if we're standing on a flat surface like this and we look out, we can see something like 3 miles. That is, if you're 6 feet tall. For me, it's more like 2 3/4 miles. But that's not really a wide enough scope to get you to see much topographic detail. If we climb up to about 500 feet, we increase our visibility to about 27 miles, which is getting far enough to be able to depict coves and things like that. If we go up to the top of a 10,000-foot mountain, like this is Mount San Jacinto outside of Palm Springs, your visibility extends to about 125 miles, which is, on a clear day, enough to be able to generate a fairly good sketch of the surrounding area if you know how to do that. I can't say that I do. If we're at 30,000 feet in an airplane, we can see something like 212 miles. And there you really begin to be able to pick out considerable topographic detail. And many of you who enjoy window seats on your flights sometimes think that it's like a map going by underneath you. Well, if we go up even higher, this is the Horn of Africa taken from the shuttle Columbia in 1993 at 163 miles up. And we're looking north. There's the Horn of Africa. This little projecting thing, I don't remember the name of it, but it's actually the easternmost point of the African continent. And from 163 miles up, you can see about 1,200 miles. So when we get out to the horizon here, we're looking into the middle of the Arabian Peninsula. And there you begin to see a real recognizable piece of geography. In fact, here's a map from the Newberry collections from a Portuguese atlas of about 1565, showing that very area. You see we have the Horn of Africa. There's that little projecting point, and there's the Arabian Peninsula. I think that's supposed to be, well, I was going to say it's Mecca, but I guess not. It's Jeddah. That's probably Jeddah. And if we were to wrap this part of the map on our aerial photograph, we'd see that kind of congruence, which, I don't know, I think is pretty amazing. Here you've got the Horn. There's this little projecting thing. Here's the island of Socotra, which belongs to Yemen. It's actually out here, but I don't know. It seems to me it's pretty good, and it makes me ask the question, how did they do that? This is the famous blue marble picture taken from Apollo 17 in 1972, and they were at a height of 28,000 miles. So here, of course, you can see the entire globe, and on this particular shot, one of the more famous ones from that mission, you can actually see the entire continent of Africa, except for a little bit obscured by clouds. This is an Italian map by a man named Forlani from about 1565, and I think you'll recognize what it shows. And in fact, if we layer it over that aerial photograph, you see that it fits fairly well. So well that we might ask, how did they do that? This is a map of, how many of you recognize this? You might want to turn your head this way. It's New England looking from the east. We're looking west. Here's Cape Cod. This is actually Lake Winnipesaukee in New Hampshire. Here's Rhode Island. I think this is the Connecticut River. It's actually the first map published in America, 1677, in John Hubbard's History of New England. We're going to lay it next to a modern satellite photo. And I think you have to agree, it's pretty remarkable. I mean, if you start looking at details, well, okay, Nantucket isn't, Martha's Vineyard and Nantucket aren't quite in the right place, and Rhode Island is actually further out there. But generally speaking, it's not bad, and you wonder how they did that. And I want to just have a little local example. This is General Smith's map of the Tennessee government. I think it's 1825. And, of course, you can see Knoxville. And here is the modern satellite image. Now, of course, I don't want to make any claims that this is an incredibly accurate map, but it does show, there's Knoxville there. It does definitely show its position between these two northeast-southwest trending rivers, and you certainly do see the northeast-southwest trending mountain lines. So, how did they do that? Well, to begin with, I want to go way back to the ancient times and answer a question that many people, I don't know, when I grew up, I learned that at the time of Columbus, everybody thought the world was flat and, you know, this kind of thing. The fact is that anybody with any scholarly pretensions or even any practical navigation experience knew very well that the world wasn't flat. But it's hard. It's a hard thing to realize that when you're standing on the world, standing on a beach. And this is a little from a cosmography, 1524, that attempts to explain to people, to give them one proof for the rotundity of the world. And what he's in effect saying here is, here's the moon, here's the Earth, and here's the sun. If the Earth were a tetrahedron or something like that, the shadow that the sun cast on the moon would be this shape. If the Earth were pyramidal, the shadow would be this shape. If the Earth were a cube, you'd get a shadow like that. But in fact, the Earth is round, and so you get a shadow like that. So it's certainly not the case that everybody knew the world was round, but it was well known. And in fact, as long ago as 200 BC, a fellow named Eratosthenes was able to actually measure, to come up with a pretty good estimate of the actual circumference of the Earth. And this is the way he did that. This is Egypt, and he understood, he knew that in Syene, a place which is actually very close to the Aswan Dam, there was a well. And on a certain day of the year, the sun was said to be directly above that well. And you knew that because if you looked down this very deep well in the desert, you could see the reflection of the sun. So he did an experiment Eratosthenes lived in Alexandria, and he did an experiment in which on the same day that well was supposed to be illuminated in that way, he measured the angle of the shadow cast by a pole, a perpendicular pole, in Alexandria. And through some fairly elementary mathematics, he assumed that, in fact, they were more or less on a north-south line, and in fact, they are more or less on a north-south line. And so he did this experiment. Here's a side view of what he did. Here's the well. Actually, this is graduated in miles. It's about 480 miles. And here in Alexandria, when the sun's rays, of course, are absolutely parallel because the sun is so far away and the Earth is so small by comparison. So when the sun's rays penetrated to the bottom of the well in Syene, they cast a shadow this big in Alexandria. And the geometry of it is pretty simple. If you measure the angle cast by the shadow, it's the same as this angle here, this sector of the Earth. And he calculated that that was 7.2 degrees, or a 50th of a circle. So if you take, he reckoned the distance as 5,000 stadia. If you take 5,000 stadia and multiply it by 50, you get a figure which, translated into miles, is about 24,860, or 24,000 miles, and the actual figure is 24,860. So he's off by 9%, but I think, you know, pretty reasonable calculation considering the instrumentation he had available. We're going to move now quickly to the first really important and in many ways the most influential cartographer who ever lived, and that's Claudius Ptolemy. He lived in the 2nd century A.D., worked right around 125 A.D. Of course, we don't really know what he looked like, but this is a 16th century imaginary portrait. And Ptolemy was a polymath. He wrote treatises on astronomy, on music, on mathematics. He's actually most known as an astronomer, probably. But one of the treatises he wrote was called Geographia, on geography, and by which he meant the mapping of the world, geography, the writing of the world. And he knew, of course, the Earth was round, and he was a sphere, and he conceived that and this was the general Greek view, that the area in which people lived, the oikoumene, was 1/4 of a sphere. And they assumed, they knew a little bit about what was down here. Well, actually they didn't, because here's the top part of Africa. They really didn't know much about that, but they assumed that there had to be 4 other pieces of a landscape on this globe to balance it out. So he came up with, one of the things he invented was this projection. This is called Ptolemy's first projection. It's a cylindrical projection, and it shows 180 degrees from his western end, which was the Fortunate Isles. People aren't sure whether, some people think it was the Canaries and Madeira. Some people think it was Cape Verde. But whatever it was sort of the farthest out thing in the Atlantic that Ptolemy and other Greek geographers knew of. And he drew it 180 degrees, in other words, halfway around the globe. And the extent north and south is from a little bit north of 60 degrees, the parallel of Thule, to the parallel opposite Meroe. Meroe is a town in North Sudan, or was a town in North Sudan, at about 15 degrees below the equator. There's the equator. No, I'm sorry, there's the equinox line. We're all north of the equator here. So his second projection is a little more, suggests a little more the globular shape. This is Ptolemy's second projection. And this is the world map that he came up with. And it shows, you know, the 180 degrees. Here are the Fortunate Isles out here, whatever they are. And you notice Africa it's pretty unknown down here. All he knew about was this part. And the assumption was that the Indian Ocean was a closed sea. Just to orient you a little bit, and of course, orient comes from the fact that many older maps were oriented with east at the top, hence orient. But to put you in the picture a little bit, this sort of misshapen thing is the Indian subcontinent, and this is the island of Sri Lanka, Ceylon. This is probably the Malay Peninsula. So he came up with a world map and also 26 regional maps. He made a map of, he made 10 maps of Europe, 4 maps of Africa, and 12 maps of Asia. Now, how did he place things. He talks actually about how to make a map, and the first thing he says is, well, because the Earth is round, you really should start with a big ball. But that's kind of difficult. It would be hard for us today, too, to start with a big blank ball. So, and then he said the next best thing is to start with a slice of a ball. You know, so you have a big curved surface like that, and then you can make your map on that. But he says that also is difficult. So let's just work with flat paper. So he comes up with these two projections, and he proceeds to plot on them all the places he knew about in the world. One of the main tools that would have been available at that time was a quadrant, looking more or less like this, a device that you could sight through on this side, and a little weighted plumb hung down. And if you sighted, say, the North Star, that would read directly to your latitude. Latitude was relatively easy. And in the ancient world, some astronomers had very huge models of these things, very large operational quadrants, and they could probably read quite accurately the latitude. Another way that he determined how far north and south a place was by knowing something about the difference between the length of day and the length of night. At the equator, it's equal. You know, a day is as long as a night. At certain times of the year. But then as you go north, here's the day of Miro, that place in northern Sudan. There's a 1 hour difference between the longest day and the shortest day. At Syene, a place in southern Egypt, there's a 2 hour difference. At Alexandria, it's about 3.5. By the time you get up here to the far north, like Denmark, it's about 9 hours or more. So this is the kind of information he would have gathered from Roman legions operating in England and Germany and Spain and France, how long the longest day was in various places. So that would be how he would set his latitude. So here this is how he would plot the latitude of. He knew that Alexandria was 31 degrees north. He knew that quite accurately. He calculated that it was about 60 degrees and 30 minutes east of the Fortunate Islands. Now, how would he have known that? He talks about one way, of course, longitude is time. 1 hour of time is 15 minutes of longitude. And what we know now that the most accurate way to understand longitude is to be able to carry an accurate clock from one place to another. And of course, it took thousands of years for that to be finalized. It wasn't until John Harrison in the 1780s that they actually had a chronometer accurate enough to carry time that way. But even in Ptolemy's day, he was aware of other solutions. He said if you had accurate information about the timing of eclipses, if you knew that an eclipse observed over here in Damascus happened at midnight, and it was observed at like 1:30 in the morning in Alexandria, or I don't know, in Cadiz or something, then you would be able to use that as an instant of time and calculate the distance. So and he had some information like that. There was a little bit of information about eclipses, but a lot of information had been gathered about the distances of places. Of course, the Romans were wandering all over their empire, and they were very active in Britain a little before Ptolemy's time, and so a place like London was nailed down. And it's probable that most of Ptolemy's longitudes are actually cobbled together from distance measurements. So from Alexandria here, he would have, of course, he had access to the Alexandrian library, which was full of information and access presumably to all sorts of Roman records and itineraries and things like that, virtually all of which is lost to us now. But he knew that, for instance, if you went from Alexandria to Algiers or Tunis, that it took, that it was so far. You know, they reckoned it was so many Roman miles. He actually had a system whereby if he had an itinerary distance between two places, he knew, of course, that any road is going to be a little windy. He allowed for 1/5 error. So he said, if he had a distance of there was 500 stadia or 500 Roman miles, say, from Alexandria to Tunis, he said, well, okay, I'm going to count that as 400. And then he would establish the longitude of Tunis, or of London, or of some other city. So in a very slow and painstaking way, I like to envision Ptolemy as working on one huge map, maybe on a wall, or maybe even more conveniently on a floor like this, and having drawn out his projection and saying, okay, here's Alexandria, and I know Damascus is this far away, and it's at this latitude, then I'm going to say it's here, and gradually shifting back and forth and moving things around, he came up with his world map, which you saw earlier. Just a sort of a sideline in a way about the discovery of America, this is a globe made in 1492 by a German named Martin Beheim, who was working in Portugal. Now, there's no evidence that Columbus ever saw this globe, although if there was one globe, there may have been more. I mean, I'm sure it wasn't a unique object. So it's not at all unlikely that he saw this globe or something like it. You know, at least this was a concept that was clearly out there. And basically what this globe does is it takes Ptolemy's world and wraps it around a globe. It happens, though, that because Ptolemy actually didn't accept Eratosthenes' measurement, apparently, for the size of the globe. I don't remember what the reasons were, but he posited a somewhat smaller sphere for the Earth, and he actually he ended up exaggerating the longitudinal length of the oikumene. So when you wrap Ptolemy's a little too large Earth around a little too small globe, you get what we would call Pacific Ocean view that looks like this. This is a projection of the Beheim globe looking with Europe over here, and here's China, and these islands off of China. Maybe that's could be the Philippines, or there's some idea of that. Here's Cipangu, which is Japan. This is all information that came from Marco Polo. But what you can see is, I love this example because it shows you exactly what Columbus thought he was doing. When he sailed from Spain, his idea was to sail west until, and these are the islands, the Canaries and the other islands in the Atlantic, was to sail past all those islands until he hit other islands off the coast of China. And indeed, he thought when he hit Hispaniola and those other places that those were some of these islands. And I believe the story is that Columbus actually went to his grave thinking that he had in fact discovered these East Indies. So I want to show you in a little more detail how Ptolemy went about mapping making one of his detailed maps. Ptolemy's first map of Europe is the British Isles, and interestingly, his arrangement of these regional maps, starting with the British Isles and the second map being the Iberian Peninsula, that tradition became very firmly entrenched, so that when the first modern atlas came out in 1570, Abraham Ortelius, he had a world map, and then his first regional map was the British Isles, and the second regional map was Iberia. And in fact, most atlases made until the 20th century followed that pattern. At least it was Great Britain, it was Spain, then it was France, and then so on. The order kind of falls apart after that. But that was how influential Ptolemy was. So this is a satellite view of Great Britain, and this is Ptolemy's map of Great Britain. And this is the kind of information that Ptolemy recorded. Lots of place names of towns, a number of locations of rivers. This interior, we're not to take this interior detail at all seriously, but supposedly the river mouth it's something that he plotted. There are some names of peoples here, sort of general names. This is where I can't read these names on here, but this is where this tribe lives, and this is where these people live. And a few physical features like some mountains and even a big forest here in Scotland. So how did he do that? Well, he started with a projection of that part of the world, and he put down his best guess as to where London was located, latitude and longitude. The British, the Roman legions, of course, were all over Great Britain, and they undoubtedly had regular travel between all these places, and he had itineraries telling him how far certain things were, especially towns. Tamara, actually, I think, is a river in Cornwall. Corinium is, I have to look at my crib sheet. Corinium is Cirencester. Maridunum is Carmarthen in Wales. This is the promontory of Kent, which was apparently fairly well established because it was where the Roman troops, the Roman ships that would be the first landfall there in Britain. And so there were a number of places that he had. Ratier is Leicester, Diva is Cheshire, Lindum is Lincoln, and Eboracum is York. And he adds the note in his geography that this is where the 6th Legion won a victory. So there were a number of places that he was able to establish fairly accurately in relation to one another where they were. And from some of these fixed locations, some people even think that the Romans had a kind of a triangulation, had a kind of a standard triangle that they worked off of here in surveying, in making maps of England. And Ptolemy may actually have had a map of England that he got from someone in the army. It's not at all unthinkable that there was a sketch map, and they said, yeah, well, this is what this southwest promontory looks like. So anyway, using the best information he had, he came up with this outline on his big map. Let's picture it on the floor here. And he also put in the river mouths. They said, well, this river is up here so many miles north of this point here, and so he plotted all these places on his map. Now, if he had just done that and made these wonderful maps, that would have been enough had they survived. But the problem with maps then and still today is that they're extremely fragile and extremely subject to wear and tear. And any of you who have a car with a glove compartment, you can testify that, in fact, most maps get used to death if they're used at all. So had Ptolemy made a big world map on parchment or on papyrus or something, and had he made a set of 26 regional maps, maybe they would have survived, maybe copies would have been made, and they would have survived the millennia. But, and he undoubtedly did make such maps. I mean, he at least made one big map, we know that. But the reason Ptolemy's geography survived is because he digitized it. He took all of these, he started with these latitudes and longitudes of towns, and then he started plotting reading off of his base map on the floor, let's say. He started reading off other coordinates. So if you'll follow these dots that I've placed around here, he would say, okay, well, at this point of this bulge, it's 53 degrees, 30 minutes of latitude and about 22 degrees, 10 minutes of longitude. And he'd write that down. And he'd do this for the river mouths, for the promontories, for all these different features around the island. And he came up with dozens, perhaps as many as a couple hundred points for the British Isles. And he recorded those in tabular format, like this. This happens to be a Latin manuscript of Ptolemy's geography. He would have written in Greek, and there are some extant Greek manuscripts. But basically, Ptolemy's geography, as we know it, as it came down through the ages consisted of no maps, but a textbook of how to do the projections and a general description of how to map, and a list of 8,000 coordinates like this. Here's a place, here's the latitude and fraction and longitude and fraction. And actually the way he indicated degrees, minutes and well, he didn't really get into seconds, but the way he indicated minutes was, he would say, if it was, we would call it 50 degrees, 30 minutes, he would say 50 degrees and a half. And if it was 50 degrees, 45 minutes, he would say 50 degrees and a half and a quarter. They didn't have the concept of unified fractions. So the geography, as it came down through the ages, consisted of just data, just alphanumeric data, digital data, if you will. And it wasn't that there is some evidence that the Arabs had access to Ptolemy's geography, but it was pretty much lost to Western culture until the late 1200s. I'm sorry, the late 1300s, when a copy was discovered in Constantinople, a Greek manuscript, and a geographer in Constantinople said, here's a direction for how to make a world map. And he proceeded to plot out these 8, having drawn, we don't know if he did one big map or made regional maps, but he followed Ptolemy's instructions. He plotted out all these 8,000 places and produced this atlas. Well, that was a revolutionary thing. And that atlas very quickly got translated into Latin, and many, many copies were made of it, and it became the first standard atlas of the world. This in about 1400. And in many ways, it stayed the standard atlas of the world for at least 100 years. Ptolemy's geography was one of the first books to be published. The first edition with maps was 1477, a very early illustrated book. And there were multiple editions all through the 16th century. It wasn't until about in 1570 when Ortelius came out with his Theatrum Orbis Terrarum. That's thought of as the first modern atlas. But until that time, at least until the 1520s, Ptolemy's maps from 125 AD were pretty much it for understanding the geography of the world. Of course, when the new discoveries happened, they had to think on their feet, and there are several maps. There's one map in particular I'm thinking of in the exhibit where you see what's basically a Ptolemaic world with some American stuff tacked on. But to get back to his map of Britain, many of you may have wondered why Scotland is bent over like that. I haven't read actually anywhere anyone saying this explicitly, but I'm pretty convinced this is what happened. If you turn that bit of Scotland up on end like this, 90 degrees, you'll see that it actually is not a bad rendition of Scotland. I mean, you get the basic peninsula up here, this Moray Firth, you get this peninsula here, these little fjord-like things over on the west side. It's not bad for 125 AD, drawn by a guy a couple thousand miles away who never left Alexandria, working from verbal descriptions probably. But the reason he had to bend it was because of the island of Thule. You remember that zonal diagram? It showed the sort of northernmost habitable place as the latitude of Thule. Well, Thule, this is from a map of 1539 showing this imaginary island. Some people think it actually might have been Iceland or possibly some other faraway island in the North Atlantic. But basically, Ptolemy's information went back to Pytheas, who said that Thule was 6 days' sail north of Britain and is near the frozen sea. And the idea was that when you got that far north, much beyond 60 degrees north, that the entire sea was frozen and it would obviously be uninhabitable. So Ptolemy was in a pickle because he had a lot of information from the Roman legions about Britain and about Scotland, and he clearly knew that when you got up here, there was still about this much more to go. But he had the problem that here was his Thule. He had plotted Thule as this location. And according to Pytheas, it had to be 6 days sail north of Britain, and if he put it up this way, it just didn't fit. So he did what a lot of scientists do today. They try to adjust, understand the data in the way that seems to make the most sense. And for him, he tries to preserve the length of Britain while at the same time recognizing that Thule is pretty much the northern limit of habitation. So he simply bent it. That's my view, and I challenge anyone if anyone has another explanation, they're welcome to give it. So anyway, this is Ptolemy's world, the same world that's wrapped around that Behaim globe, although the Behaim globe also includes information from Marco Polo, which extends China out here and gives us Japan. Moving now to the middle, to the Mediterranean, we're going to talk about another great Ptolemy's, the discovery of Ptolemy's geography in 1400 or thereabouts is just an epical thing in the history of cartography. The whole idea of mapping on a grid, latitude and longitude, that all comes from Ptolemy. But there was another tradition that had started a couple hundred years earlier, that in the Mediterranean, that is sort of a parallel tradition, and that's the tradition of the Portolan chart. This is the earliest known copy of a Portolan chart, and some of the characteristics of Portolan charts, well, they're almost always drawn on an animal skin, on vellum. This is the neck of the animal. If you can you see the outline here? Here, we're looking at the Mediterranean. Down here is the Strait of Gibraltar, and here's North Africa. Here's the boot of Italy. Here's the eastern shore of the Mediterranean, and actually the Black Sea was almost always included in Portolan charts, and the Black Sea has been somewhat eroded here. Actually, this map, one of the most important maps in the history of cartography, was found in a Paris junk shop in 1840-something, and it now lives in the Bibliothèque Nationale. Here's a detail of the carte paysanne, as it's called, which shows you in greater detail some of the characteristics. Portolan charts invariably have a circular grid. If you step back, you can actually see a couple of great circles here inscribed that have wind roses in the middle and radiating wind lines, or rum lines as they're called, R-H-U-M-B. The place names on Portolan charts are always written inland. They tried to leave the water spaces as open as possible. Typically, the rum lines were different colors. Some were green, some were red. Some charts have black ones. Another characteristic. They show tiny little rocks. There's another example. I can show you some more symbols. But and the other thing is that there is no up on a Portolan chart. There's just no. You can't say, oh, this is meant to be up. The lettering, if you'll see, these are meant to be read from that way. And then down here, I can't quite make that out. They're still read that way, but over here they're read this way. And if you go around an island, you have to you'd have to kind of turn the chart around like that. So it didn't really have a natural up. This is another Portolan chart. This is from the Newberry's collection. This is our earliest Portolan. We have a couple dozen Portolan charts and atlases. This is 1456, done by Rosselli from Mallorca. He signs it up here in the neck. And again, it's the outline of the Mediterranean with the Black Sea. Some of them also went up, most of them went up the west coast of Europe, included the British Isles usually. Very often they would put these maps, these flags around the border. Many of the portolan charts that have survived, obviously the carte paysanne is a pretty tattered and torn thing, and was not probably terribly attractive when it was made. Some of the portolan charts that have survived are very pristine, lovely things that probably were made for rich clients or for parlor use or library use. But there are some that give evidence of having been to sea, and I think this is one of them. Over here on this side, there are these holes. That's where it was nailed onto a wooden roller. And over here on the neck is a little hole. There would have been a leather thong through there, so you'd roll it up and tie it with that thong and stick it in a cubbyhole on board ship. And it's definitely seen some wear here from being rolled and unrolled, and even some of these flags have obvious signs of the ink, the pigment having gotten wet. So I don't know. I like to think this one may actually have gone to sea. Anyway, how were they used? This is another portolan atlas from the Newberry. It's actually this is an atlas. This is an opening of 2 pages. I've had to join the sheets here, the digital copies. But to show you how a mariner might use a portolan chart like this, if you wanted to go from this Melilla, I think it is, on the north coast of Africa, to this point over here, Cabo da Gata, Cape of Cat Cape. In other words, he wanted to sail a course more or less like that. He could draw his course on there, or lay a parallel ruler between those places. There's one side of the parallel ruler, and then he'd swing out the other arm of the ruler until he lined it up with a windrose. And in this case, as you can see, that's the north line, north by east, north-northeast. It's actually in between north by east and north-northeast. So the mariner starting out from here would try to get his compass to read a little bit east of north by east, and hopefully would strike this point. But hopefully not literally, because as a matter of fact, there's an indication here that there's a big rock there. And I think if you're familiar with modern nautical charts, I think something very like that is used today to indicate a hazard to navigation, like a rock. Little dots like this to indicate shoals. Some of these portolan charts even have a little ship's skeleton to indicate a wreck, a sunken ship. So the main tool was a compass, such as this one. We don't really have any really ancient compasses. The compass was, they used to say that it was invented in China and carried to the Mediterranean. Now people think that it may have been independently invented. But anyway, there's textual evidence that people talking about sailing with compasses, sailing by the magnetized needle in the early 1200s. And so that's about the time the carte paysanne comes out, sometime in the late 1200s. The earliest compasses may have been just a needle actually floating on water, held up by surface tension. Sometimes they would push the needle through a straw, and that would keep it afloat. But I'm sure by a very early age they had devised this method of a card with the needle attached underneath. And they would have needed an hourglass, or in some cases a minute glass or a half-minute glass. And navigators from at least the late Middle Ages up until well into the 18th century were using a log and line to gather information about their speed. Basically, you needed a spool with a lot of line on it. You needed this log here, or chip, and you needed a glass that was good for half a minute. And the way it worked was something like this. I think you must have needed at least 3 men. One guy is holding the log reel. Another guy is holding the 30-second glass, and another guy is holding the actual chip here, which is weighted at the bottom. He throws this thing over the back of the ship, and it hits the water and starts bobbing along. And of course, the water catches it here, so it's sort of riding up in the water. And he waits until about the length of the ship. There's a red rag tied there. And that indicates that the thing is now far enough behind the ship so that it's free of the wake of the ship, and supposedly it's kind of digging into more untroubled waters. And when that red line goes over the rail, he says, "Turn." And the guy with the 30-second glass turns the glass, and then they start counting how many knots go over. And the knots are placed, well, apparently there were a couple different lengths of knot, but the knots are placed at regular intervals along there. And you count how many knots go over, and when the glass runs out, the guy says, "Stop." And then the guy holding the reel holds it. They count how many knots have gone over, and they record that information on this device, which is a Travers board. And this is a wonderfully simple device that didn't require any great learning. An illiterate seaman could use it as long as he was familiar with the points of the compass and could read the numbers, I guess, from 1 to 12. The idea is this. Here are all the points of the compass that you could possibly steer. Each of these concentric rows of circles is a half hour. So this would be the first half hour of a watch, the second half hour, the third half hour, and so on, up to the 4-hour watch. A very standard way of breaking up the day at sea from early on. And attached to the middle, there's a cord, and you have a bunch of little pegs to go along with it, which you can push next to the cord into a hole. So what this tells us is that in the first half hour of the watch, they were sailing north by west on that course. And in the second half hour of the watch, they were still sailing north by west. But when the third half hour came along, they had shifted their course to this point of the compass. And in the fourth half hour, after 2 hours of sailing, they had shifted it to this point. So you'd keep doing this, and for the 4 hours of a watch, you'd have a perfect record of the course you had steered. Now, how fast were you going? Well, every hour, they would do this business with the log, the chip log, and they would plot those down here. Each of these lines is 1 hour of the watch. That's the first hour, the second hour, the third hour, the fourth hour. What this tells us is that in the first hour of the watch, they were going 6 knots. So they put the little peg there. In the second hour of the watch, I'm doing all this pointing, and I made this elaborate slide to show you this. I forgot about it. So there's the first hour, 6 knots. In the second hour, 8 knots, but a little more than 8 knots. In fact, 8.5 knots. They could record down to the quarter of a knot. So that's a fairly good, fairly accurate estimate of your speed. So at the end of a 4-hour watch, the seaman could hand this board over to the captain or whoever was keeping the records, and they would have a complete record of distance and direction and speed for that watch, which they could write down into a log. Well, how did Portland? I see Jeff looking at his watch. Yeah, okay, that clock is right. I'm doing all right. How did this information get recorded? Ultimately, a lot of seamen's information about distances from ports and things like that got recorded in itinerary form like this. It's strictly, well, I will call it again a digital record. I mean, it certainly uses numbers. Here's there are Roman numerals in here, and alphanumeric characters to record certain information, and this is the kind of information they record. These are called portolani, books of sailing directions between ports. And this is the most famous portolani is the Compasso de Navigare from the late 1200s. And here's just one of the indications. They go from Fanaro, this port, to Felia. It's 30 miles to the northwest. And then there's sometimes notes about the place. But it's just one thing like that after another going around the whole course of the Mediterranean and the Black Sea. That's what's in the Compasso da Navigare. Now, people have long imagined that there had to be some connection between these portolani, these books of directions like that, and the finished Portolan charts. But it wasn't until a couple decades ago that a retired physician, Jonathan Landman, actually took the trouble to convert all of the measurements, all of the information in the Compasso da Navigare into distances, standard distances, and directions. He took, and when he read northwest, he turned that into so many degrees. When he read north by northwest, he converted that into so many degrees. And then he plotted down the distances and those bearings and started to see what would happen. And in fact, he discovered that the Compasso da Navigare, if you plot down all those distances and directions, it does in fact, I didn't mean to do that. What do I do? Just do this? Yeah. It does in fact generate a map of the Mediterranean. Now, of course, it didn't come out exactly like this. Any of you know anything about surveying know that there's something called error of closure. Whenever you survey around an area, it's not going to end up perfectly like that. In fact, this may be way down here or something. But as long as you're working with a closed area, and this is virtually closed here at the Strait of Gibraltar, you know how to adjust it. So you just kind of adjust a little bit on every angle to make it fit like this. Well, how close was it? Well, it was pretty close. There's the modern outline of the Mediterranean. So we're pretty sure this is how the basic Portolan chart was generated from these tables, really, or verbal lists of distances and directions. And of course, it didn't happen all at once like that. It wasn't that there was suddenly this Compasso da Navigare, and somebody took that and plotted it, and voila, Portolan chart. I mean, it must have been a long procedure involving many errors and many partial maps, I suppose, of different areas. But it's pretty clear, I think, that is the source. And now I'm going to say a little bit about a more continental approach. The Mediterranean, we discovered, is pretty much mapped through very accurate, very small-scale measurements of distance and direction around the perimeter. Much the same thing, using many of the same instruments, is happening on a larger scale when we come to a continent. We've already seen one early map of this part of Africa. Now we're going to look at some of the Portuguese efforts to map the west coast of Africa. Now, another instrument that would have been involved besides the quadrant that we saw, Ptolemy was holding a quadrant. There was an instrument called the cross staff, which works the same way. You sight an object, and you align this bar of this thing with the horizon, and this top of the bar with whatever you're sighting, North Star or Sun, and you read an angle off of this sliding bar. There's a model in the exhibit here. There are lots of wonderful instruments in this exhibit that are, some of which I've never seen before. Very neat addition to the exhibit. And in there is a back staff, which is the same principle as this cross staff, but instead of having to look directly at the sun, you turn your back to the sun, and this has a little mirror on it here, or a little vane, and you can read the shadow, the shadow of the sun instead of directly. But it accomplishes the same thing. So using logs and lines and instruments like the quadrant or the cross staff to measure latitude, the Portuguese gradually began to map Africa. Now this is a portion of a 1489 map, and I've trimmed everything else away except what Ptolemy knew. This is pretty much the Africa that Ptolemy knew. It consisted of the the north coast here, the north shore of the Mediterranean. He knew about the Atlas Mountains. He knew about the Nile, and they knew or thought they knew that the Nile had its source in the mountains of the moon, somewhere way down south in Africa. They also knew or thought they knew about some big lakes here, which I have no doubt were Lake Victoria and Lake Nyasaland, or whatever those lakes are. The word was there were big lakes down there at the Nile, towards the end of the Nile. So that was Ptolemy's Africa. Well, by the time the Portuguese really started to make a dedicated effort to try to see if they could get around Africa, if it was in fact if it in fact did not enclose the Indian Ocean, they started to sail down the west coast, and this was a very long process. I mean, 1432, another few years later, they get a little further to the River of Gold. Now we're 10 years later. Here we're a long time later. It took the Portuguese something like 50 years to get the bulge of Africa really nailed down. So they would have done this in exactly the same way by getting latitude readings on these various river mouths and things like that, and then by keeping track of their distances and directions. And finally, the big push to see if they couldn't get around the continent, and in 1487-8, Bartolomeo Diaz actually rounds the Cape of Good Hope and gets as far as the Great Fish River, where he can see the coastline trending north. So this is the Africa that is known after Diaz's expedition, 1488. And in fact, this map is a world map made by a German called Henricus Martellus in 1489. This is a manuscript at the British Library. There's another copy of the Martellus map with very much the same geography at Yale. And of course you can see this is still Ptolemy's truncated South Asia and his very huge Ceylon, Taprobana. But here it does have some indication that there is, from Marco Polo, that there are these islands off the coast of China. So that is how continents are mapped in a very basic way, and that is how North America ultimately was mapped too. Now I want to conclude with a case study of how the interior of continents might have been mapped, and or was, in this case, how it was mapped. These are the Great Lakes, of course, and I think you can see that it would be a much different proposition to try to map the Great Lakes by coming in here and making a circuit of the lake and then measuring this distance down here and then making a circuit of this lake and circuit of this lake and stringing those all together into in the way we did with the Mediterranean. That would have been a tall order. And in fact, it didn't happen because the only people on these lakes for hundreds of years were voyageurs in birch bark canoes. So you ended up with fairly crude maps of the Great Lakes. This is actually the first map to show all 5 of the Great Lakes. And you can see Lake Superior, they obviously were up here near the Straits of Mackinac, and they knew there was a big lake opening up there, but they didn't know how big or where it ended. This is presumably Lake Michigan, although Lac de Pouan, the name of Green Bay, is usually Bay de Pouan. So that would be Lake Michigan, Huron, Ontario, and Erie. But I'm showing you a series of maps that attempt to represent the Great Lakes to show you that there's no such thing as nice linear progressions in cartography. We like to think that in general, every map is an improvement on the last map, and I suppose in some cases that is the case, But if you look at a lot of early maps, you'll see a lot of stumbling, a lot of just plain, I don't know, making things up. Cartographers have always borrowed wildly from other cartographers. I mean, until very recently, when we can actually go to something like Google Earth or NASA and get, or this digital image laboratory, and get up-to-date photographs of the Earth's surface. Until very recently, when a cartographer was asked to make a map of such and such area, the first thing he did was find another map of that area and use it as a base map and maybe adapt it or change the scale or something like that. Most maps are actually made from other maps. And at this time, too, people were copying each other. So as we go through these various images of the Great Lakes, you'll see some things that look the same. You'll say, oh, that looks like he copied that from so-and-so. One of the things that I'm always interested in is when it comes to the Great Lakes, if you can define the shape of Michigan, both its southern peninsula and its northern peninsula, you have almost completed a map of the Great Lakes. And if you'll watch Michigan through this series of slides, I think you'll see that it was a very hard little peninsula to map. Surprisingly, this is a nice example of how progression is not linear in cartography. This happens to be a very early, in fact, the first map of Lake Superior, 1671. We know it was done by the Jesuits. It's published in the Jesuit Relations. We don't really know who did it. Father Alouez was one. I think Father Marquette may actually have been involved. He was up here at the mission on the Apostle Islands. But it's actually a very accurate map of Lake Superior. It has Isle Royale here. It has just a couple of little minor islands that are actually there. And the reason they were able to do this is we know that the Jesuits actually made a pretty much complete circuit of the lake in canoes, counting paddle strokes perhaps, I don't know, but estimating the distance in some way, and taking readings of latitude with an astrolabe or with a quadrant. Here again, Michigan is a little distorted. Look at Lake Michigan. On many of these early maps, actually there are some where it's swinging way this way, somewhere it's almost straight up and down, and somewhere it's way over at this angle. Michigan is like a pendulum. Franquelin, very influential French map maker. He seems to have relied, I think, a little bit on the Jesuit map. He knew about it anyway. Coronelli, Italian cartographer, 1680s. This looks like it's copied from the Jesuit map, except for some reason he thought he had to make it much wider. Some fairly outlandish figures here. Where this comes from, this is the beginning of adding islands to Lake Superior. In the late 17th century, there were a couple of French manuscript maps made that just suddenly put in imaginary islands and named them after influential characters in France. And those islands got picked up on later maps. It's always the bad stuff that gets copied first. So these depictions, I don't know where they come from. Hennepin was generally not considered a very reliable traveler or cartographer. Delisle was one of the best map makers, and actually it's not a bad representation of the Great Lakes. He's clearly using the Jesuit map here for Lake Superior, and Lake Michigan is actually fairly reasonably oriented. Herman Moll, one of the more imaginative cartographers. Captain Cyprian Southack, the first map of North America published in America, published in Boston in 1717, but where he got his Great Lakes from, I do not know. Very strange. I don't think there was a model for that. Popple, a part of Henry Popple's map, the southern sheets showing the Gulf of Mexico, is in the exhibit. One of the best maps of North America in the 18th century. I have fairly reasonable Michigan and Lake Michigan, but notice Lake Superior. Here he's got this is Isle Royale, and then here's Isle Philippot, Pontchartrain, and I can't quite read it, but there were 3 or 4 or 5 islands just thrown in there to flatter the French officials. In fact, each one is named after another official. So it's nice to have an island named after you. Here again, Lake Michigan, way off to the southwest, and Michigan Peninsula, just a little point. This is the Mitchell map, the second, maybe the most important 18th century map of North America. It's been called the most important map in American history, largely because this is the map that in 1783 was laying in front of the commissioners in Paris who drew the Treaty of Peace, and they drew a red line on this map showing the border dividing the United States from British colonies. Mitchell's map is interesting in that this is this is actually the Newberry's copy, badly reproduced, but our copy is colored so that you can see that the colonies were, at least the southern colonies, were shown with their western borders extending to the Pacific, according to the colonial charters. There's a wonderful copy of the Mitchell map upstairs in the exhibit, too. It isn't colored quite this dramatically, but if you see, the Charter of North Carolina colony was supposed to extend to the Pacific. Now, if you're wondering where western Tennessee would have been had that actually happened, this is how it would sort out. Monterey would be in West Tennessee, and San Luis Obispo, nice wine country in there. Could have been great. So a couple more maps attempting to show the Great Lakes. I'm gonna concentrate on a couple of maps by this English cartographer named John Carey, who publishes a series of maps of regions of the United States like this, beginning in 1805. And I guess if you look at the great, well, they're recognizable, and he's gotten rid of the fake. No, he hasn't gotten rid of the fake islands. They're still there. There's Royale, but there's Philippot. In fact, this actually went back to the Mitchell map. The Mitchell map was used, as I said, to draw the Treaty of Peace. Can I get back there? How far away was it? It's when they drew the line for the border, they drew it up here, and they said, okay, they drew it across this island and to Isle Royale, and they went south of Isle Royale, and then they went up a river here. And in the treaty, it said, north of the Isles Philippot and Pontchartrain and Isle Royale or something. And so they cited in the actual treaty document 2 islands that just didn't exist. And so for the next 70 years, they were looking, and the British were arguing that, oh, this is what Isle Pontchartrain was, and the Americans said, no, it was this island, and finally it took a long. It wasn't until the 1840s when they finally ruled that, in fact, those islands didn't exist. But here they are, 1805. It still shows the border going across this non-existent island. So anyway, this is Carey's 1805 map, and that would have served fine, except when in 1805 Ohio became a state, and so in later editions he had to add Ohio. Here the general geography is pretty good. There's Chicago, the Portage, St. Joseph, Michigan, Detroit. But when he got to 1825, by that time there were already, Ohio had become a state, Indiana had become a state, Illinois had become a state, and he had to fit them in somehow. He didn't change the basic geography. He didn't have any better information. But you can see it gave him some problems because here, for instance, is the bottom of Lake Michigan. Well, Illinois, first of all, is landlocked. It has no lake. This is Illinois. Fort Dearborn in Chicago is in Wisconsin, what's now Wisconsin. Indiana is here. It was very hard to fit in, and the reason was he actually had a very good observation for the. Oh yeah, this is indicating his basic difficulty. How do you fit 3 states like that into that space between the Mississippi and the western border of Pennsylvania. Now he knew for a certainty about, his longitude for the west end of Lake Superior is pretty good. It's actually right about 92 degrees west, which is what he shows. His longitude for the east end of Lake Ontario is also right on. Also, the western border of Pennsylvania. And the reason that's right on is because of the Mason-Dixon line, which of course was surveyed on the ground with guys lugging chains and blazing through trees and making paths and marking on the ground the how many 100 miles to the western border of Pennsylvania. So he had those things pretty well fixed. But he was very vague about the Mississippi River. There weren't any accurate observations out there. And this lake system in here was just very, very little known. That's the western border of Ohio. This is the western border of Indiana. And this is the westernmost bulge of Illinois on the Mississippi. So how did this little problem gets solved? Well, unlike our other examples, it wasn't solved from the water, it was solved on land. And it was solved by people dragging chains like this across the country and orienting them with compasses like this. The general, in the Northwest Territory, which was this area here, was decided to divide it completely into parcels. Of course, you folks down here, you have the meets and bounds system, where you just sort of said from this tree to that rock to the river and then back this far. But they decided they wanted something a little more orderly for the Northwest Territories, and so they devised this system of public lands consisting of 6-mile square townships and divided into 36 square sections. And they first did this in the very eastern part of Ohio in what was called the Seven Ranges. That was done in 1787. They were just kind of experimenting, really. They didn't quite know how they were going to expand this grid across the Northwest Territories, but and Ohio is really very much an experiment. If you look at the land surveys of Ohio, there are slightly different orientations, and they don't match up perfectly. They didn't really have a standard meridian. But by the time they got into Indiana, they started establishing a standard meridian. So you'd have one north-south line where you would number all the ranges and all the townships. And Indiana and Illinois were both settled from the south, so they became states 1816, 1818, but at the time they attained statehood, the whole northern part of the states they weren't unpopulated, but they were lightly populated and did not have the benefit of the township and range surveys. In Illinois, by 1830 they had actually surveyed a little extension up here because they wanted to build a canal from Chicago down to the Illinois River, the Illinois-Michigan Canal. And so they divided that, and the federal government started getting rid of that land. Meanwhile, on either side of it, it was still Indian country. So as these surveys progressed, they bumped up into the water. And it was only really when this survey got up here in about 1830 that they were able to say with considerable certainty and accuracy, this is where the western shore of Lake Michigan hits at that point. And as the survey continues, Wisconsin becomes a state in 48. Gradually, the entire lower peninsula of Michigan and, of course, the entire Lake Michigan and the location of the Mississippi River, they're all determined accurately by measurements on the ground. Briefly, this is what happened. Starting with the Mason-Dixon line, which after all starts in tidewater and was measured by chain and compass, and then extending the General Land Office surveys west and north and east and west, they finally we're able to determine the outline of the Great Lakes. And that's how this little bit of geography got mapped, strictly from the land. So that's all I have to say, but I'm happy to answer questions if you have any. I'll try to answer them, that is. Yes?